Okay, if you recall, a while back we talked about first integrals, which are conserved quantities, associated dynamical systems, and we sort of discussed them in the context of this notion of pullbacks with respect to the flow map. Okay, so we would like to basically do the same thing now for Hamiltonian systems, the associated flow maps, and this geometric quantity known as the symplectic two form. But in order to make sense of the symplectic form being preserved, in the sense of pullbacks, we first have to introduce the notion of what is called a tangent lift of a map. Okay, so the tangent lift of a map. Okay, and the idea, if you will, is that if you're given a map, let's call it F, from some space to itself, we'd like to see what this map induces at the level of vectors on this configuration space Q, right? So we want to sort of consider the induced map which is oftentimes denoted TF, okay, at the level of tangent spaces. Okay, so if the claim is that if you have a map, again, at the level of positions, on some manifold, then that induces in a very natural way a map at the level of vectors on the manifold. Okay, so how do you do this? So first, in order to do this, we have to ask ourselves, what do we really mean by a vector and on a manifold? Okay, so there's a nice way of thinking about vectors in terms of equivalence classes of curves, and that's going to very, very naturally lead to this idea of this induced map, which is what is called the tangent lift. Okay, so this induced map is called the tangent lift, and we'll see how you do this. So the basic idea is the following: if you have a manifold Q, all right, and you have a point on the manifold, little q, and you have a vector, let's say v sub q, associated or sort of based at that point, then what you would like to do is you would like to, okay, so vq is a element of the tangent space at the point q to the configuration manifold q, and you want to associate to this, with an equivalence class of curves. Okay. Right, with the property that the curve, when evaluated at 0, gives me the point Q. Okay, so I should say that this curve is a map from some interval contained in the rails, and which also contains it's like the point 0, and this is an open set, right? And it maps to the manifold Q. Okay, so all right, so you have this class of curves, and you want the curve that a property that when you evaluate it at 0, you get the point Q, and there's a sense in which if you differentiate this with respect to the parametrization and then evaluate it at 0, you get the vector v, if you will. Okay, so more or less what I'm saying is that there is a family of curves, all right, with the property that at the origin, at time equals to 0, more or less, it's like you get a point Q. And if you were to differentiate a curve and evaluate it at time 0, you get something which is in this direction of the vector. Okay, so that's sort of intuitively, it's like what you want to do. It's like you want to identify vectors. It's like with families of curves which have this property. Of course, it's like, it's like this doesn't uniquely specify the curve. And more or less, it's like one way of thinking about this is that you're only specifying the first two terms in the Taylor expansion, if you will, of the curve. And so it's like if you look at the higher order terms, you are allowed you know, and freedom, it's like to pick that, right? So, so this, you know, you would expect that there's more than one curve which satisfies that properties, and you want to identify all the curves, it's like which just have, you know, these two first terms in the Taylor expansion. Okay. So that's one way, if you will, of thinking about curves. It's like, and it's a very nice way. Particularly, it's like when trying to make sense of the map, which is induced by a map at the level of points in the curve, right? Okay. So why is that? And that's because, you know, again, you have this interval, right, and you have a map, which is the curve itself, to Q, and then you have this map F, right? You have this map F, which maps Q to itself. Okay, so that induces a new curve, right? Which is basically F composed with, you know, it's like this original map applied to this point, right? And this is a new curve, and you can ask what the vector associated with this new curve is. Okay, so you can look at this at the level of equivalence classes, right? So, so the idea, if you will, is that given v of q in the tangent space at q to q, right, you consider the equivalence class, right, of curves, right, and then you're sort of defining T of f acting on this equivalence class of curves, right, to be the equivalence class of curves of this composition, right? So f composed with the map, and then you take that equivalence class. Okay, and again, it's like that's sort of well defined. It's like before you take equivalence classes, because you know your map is a map from the interval. It's like some interval. It's like to Q, and then F is a map from Q to Q itself, right? So you can look at the composition of this, and then ask what is the vector associated with that. Okay. All right. So let's try to be more precise now. So you might ask, well, how do you go about doing this, right? Well, what does it? How do you do this? And the way you do this is again very, very simple, right? Because if you have this equivalence class of curves, right, and you want to get back to, you know, VQ, it's like, which is in the tangent space of Q at Q, right? And what do, right? You take that curve and you evaluate it at 0, and that's going to be Q more or less. And if you differentiate that and you evaluate it at 0, you're going to get this V, right? So that's sort of intuitively what you do. It's like in coordinates, okay, and all this turns out to make sense. So if you ask what is this composition F composed with the original curve, okay, what vector is this, right? So this is an element of TQ, but what is it? Okay, what you do is you do the same thing. You take this, you evaluate it at 0, you differentiate it, you evaluate it at 0. So you have F composed with the map, the original curve, you evaluate it at 0. So this is just F evaluated at Q, right? Because you know that the curve evaluated at 0 is Q. So it's F at Q, all right? So that makes sense. The base point of this map, right, is now F of Q, right? So what you're saying is that TF, right, is more or less a map, and let's just say I specify an initial point Q. TF is a map from TQF to TF of Q. Okay, sorry. So TF at the point Q is a map from TQ at a point Q to TQ at a point F of Q, right? So that makes perfectly reasonable sense. Okay, and then the other thing you want to do is you want to differentiate this, evaluate it at 0, and then this is going to be something like the velocity, right? So V tilde, if you will. Okay. Okay. So you apply the chain rule to this, right? So you take the linearization of F as a map, right? So this is just some linear operator now, acting on the derivative, it's like of the original curve evaluated at 0, but the derivative of the original curve evaluated at 0 is this V, right? So what that is saying is that you have dF acting on V. Okay, so that tells you that if you take TF acting on the point Q and V, right, you get f of q, and then the linearization of the map applied to the vector v, okay, which is again very, very natural. Okay, so so that's basically what is going on here. Okay, so this is what is called the tangent lift, right? So this is the tangent lift of the map f, which originally was a map from Q to Q. Okay. Then once you have the tangent lift, then we can talk about what it means for a Hamiltonian flow map to be symplectic. Okay. So symplecticity, what does that mean? Okay, so a flow map, okay, is symplectic if the following is true, right? That the pullback of the symplectic form is the symplectic form itself. Okay, and again, this is very, very analogous to what we've seen before. It's like in terms of first integrals and flow maps, right? The idea that a first integral is something where if you pull it back by the flow map, it stays invariant. Okay, so what does this mean in coordinates? So in coordinates, this means the following. Right, so if you take omega acting on two vectors v and w, right, so I'm going to write this now in terms of our expression in terms of bilinear forms and this J symplectic matrix, right? So this is just V transpose J W on the one hand, but this is equal to the pullback, right, of the symplectic form acting on V and W. Okay, and if you recall, the idea of the pullback basically is to use the map, okay, the flow map, to act on the inputs to the quantity you're working with. Okay, and in so doing, right, you have now something which makes sense on, you know, it's like on the original space, the source space, it's like of the map. Okay, whereas initially you started at the target space. So, all right, so you want to have the flow map acting on V and W, okay? But V and W are vectors, right? And the flow map is a map from T star Q to T star Q, and these are elements of T star Q, okay? So what you need to do is you need to take the tangent lift of this map and you act on these vectors, okay? So by definition, this is equal to omega acting on the tangent lift, okay, acting on V, and then the tangent lift acting on W. Okay, and then in coordinates, right, if you recall, it's like this basically just gives you the linearization of the flow map acting on V and the linearization of the flow map acting on W. So this is just omega. So there's a slight abuse of notation, but never mind. So you have the linearization of the flow map acting on V, and then the linearization of the flow map acting on W, right? And then now you can again write this in terms of the bilinear form and the J symplectic matrix, right? So this is just all right, this acting on V, okay, transpose J, and then again the linearization acting on W now. Okay, and then, okay, so I have a matrix times a vector, and I take its transpose, so I can rewrite it in the following way. I can write this as V transpose the linearization of the map transpose J, and then the linearization of the map times W. Okay. All right. So if you follow the line of equalities, you want this to be true for all V's and W's. So what that more or less says is that the J symplectic matrix has to equal to something like the conjugation of the J symplectic matrix by the linearization of the flow map. Okay. So you want this to hold for all v and w. Okay, so we obtain the condition that J is equal to the linearization of the flow map transpose J, the linearization of the flow map. Okay, so this is the condition. It's like you check, if you will, or at least a sort of a coordinate representation. You can check. It's like to say whether or not a particular flow is symplectic. Okay, so this is the familiar coordinate expression for symplecticity of the flow. Okay, and again, if you preferred, it's like sort of, to write this in a more sort of sort of a more abstract sort of setting, it's like which is independent of the choice of coordinates, then you would say that again the pullback of the symplectic form is the symplectic form. So these two things are equivalent to each other. Okay, so you should think of this as a coordinate representation of this condition here. Okay, so let's stop here for now.